In the last lecture, we talked about the importance of global mean temperature of the earth because it affects climate everywhere. Now, I mentioned that the global mean temperature of the earth is controlled mainly by carbon dioxide. This is surprising because the amount of carbon dioxide in the earth's atmosphere is much smaller than the amount of water vapor. Both water vapor and carbon dioxide affect Earth's climate, but carbon dioxide is the controller because carbon dioxide does not condense. It remains as a gas in the atmosphere. Water vapor, on the other hand, exists in all three phases. It exists as vapor, as liquid, and as ice. So, water vapor also affects Earth's climate, but the amount of water vapor, ice, and liquid water which is present on Earth depends on temperature, and that temperature is controlled by carbon dioxide. So, carbon dioxide has an unusual impact on Earth's climate, although it is a very minor gas. Now, this is not easy to understand, and that is why you need a good background in thermal radiation heat transfer to appreciate how carbon dioxide, although it is a minor gas, has a major influence on the Earth's climate. And so, that will be the focus of the lecture today. And so, we need a basic background in radiation heat transfer, and for that I am going to use two books which have been around. One is Thermal Radiation Heat Transfer by Hubble, Menguik, and Siegel. This work was published more than 50 years ago. They are in the 6th edition, and any of you can locate this book through an internet search, and you can use any edition version because this course is based on the earlier version of the book, which is somewhat simpler. The newer version is more complex. There is one more book which is relevant to this course. There is a book called An Introduction to Atmospheric Radiation by K. N. Liu, and the major model I am going to use in this course is based on a chapter in this book. Now, we start with the basics. When you talk about radiation, it is characterized by photons which are emitted and absorbed in any surface, and these photons are characterized by a wavelength and a frequency. And all of you know from your school physics background that the product of wavelength and the frequency is the speed of the propagation of the radiation in the medium. Okay. Normally, wavelength is measured in microns, which is 1/1,000,000th of a meter. Wave number is measured as 1 over wavelength in meter minus 1. Some books will talk about centimeter minus 1. Frequency is 1 over second, it is called hertz, is well known to you, and see the speed of the electromagnetic wave, and all of you know that value is constant. It is a universal constant, does not change in vacuum. Now, the range of radiation that is there in the earth is a wide range, goes from X-rays in the low wavelength range 0.02 micron all the way to microwaves, which is more than 1000 microns. As far as this course is concerned, we will be focusing mainly on radiation, the visible and the infrared. The incoming sun's radiation is primarily in the visible and little bit in the infrared, while the radiation emitted by Earth's surface and the atmosphere is in the range from around 4 microns to 100 microns. So, we have to understand how radiation from the sun is absorbed by the atmosphere and the earth, and how the radiation emitted by Earth's surface is absorbed by the atmosphere and also emitted to space. Now, so we will talk about solar radiation and Earth's long wave radiation in this course. Now, the most fundamental quantity in radiation is the emissive power, amount of radiation emitted per unit surface area, and the most fundamental quantity is defined for every angle denoted by prime and every wavelength denoted by lambda. So, you must know this definition. This definition is amount of radiation emitted per unit angle per unit area per unit wavelength. So, divided by area of the surface, the wavelength interval we are interested in, and the solid angle. Solid angle is a very fundamental concept in radiation, because photons are emitted in all the 4 pi directions. You look at this figure, photons are emitted right perpendicular as well as all the other angles, plus all other angles phi, which is called the azimuth angle. So, radiation emitted, you have to define for every angle phi and every angle theta. Okay? And so, this is to be understood that this is the basic 3-dimensional nature of radiation. So, we have to define an angle called solid angle. Solid angle is an extension of the idea of angle which you learned in high school physics. All of you know is angle d theta is the arc length ds divided by the distance from the origin r. This all of you know. This idea is now extended to more than one dimension. We have r d theta, the distance from the origin and when the angle is set by d theta, and r sin theta d phi when phi is changed. So, if you multiply these two, you get the area of this element, and that is r d theta r sin phi d phi. Divide that with the distance from the origin, which is r squared here, because there are 2 dimensions. So, this is solid angle. So, you know that the angle that you learned in high school physics goes by 360 degrees in a circle, but in the case of solid angle you go through 4 pi radians, okay, because the entire hemisphere here is 2 pi, and you can also go down in the lower region also. So, it is a whole sphere. So, sphere is 4 pi, hemisphere is 2 pi. Okay. So, this is a basic feature of radiation which all of you must appreciate and understand, because everything depends on 3 dimensions. Of course, we will make the problem simple by averaging over various angles, so that we deal with a much simpler problem later. Now, although emissive power is the basic definition of radiation emitted per unit surface area per unit solid angle per unit wavelength, there is one more quantity of equal importance called intensity. The only difference between intensity and emissive power is the use of cos theta. That is, instead of dividing by surface area, we divide by the area projected normal to the wave. So, when the radiation is leaving at this angle theta, you only look at the area, not the surface area, but the area normal to the wave, which is d a cos theta. Okay. So, that is the only difference, and you might ask why are they doing that. You will find later that for many surfaces this quantity I prime lambda, that is directional spectral intensity, is independent of angle theta and phi. That makes life very easy. If something is independent of angle theta and phi, when you integrate over these angles, it is not playing a role, it can be taken out. So, we are going to use intensity emitted by any surface to be independent of angle theta and phi. This is strictly not true. There are surfaces which emit radiation whose intensity varies with angle, but for this first course we will neglect that. Okay? We will neglect the angular variation of intensity with theta and phi and treat I prime lambda as independent of theta and phi. Okay? But note that by definition the relation between directional spectral emissive power and directional spectral intensity is this quantity, that is, you take intensity and multiply cos theta, you get emissive power just from definition. There is nothing special about it. You look at the two definition, divide one by the other, you get this. So, although we are going to assume that directional spectral intensity is independent angle theta and phi, the directional spectral emissive power is a function of theta. Okay. This will be a function of theta for any surface for which this is independent of theta and phi. Okay. So, this is a basic relationship obtained from definition, and this you must remember. The difference is intensity is defined per unit area normal to the rays, emissive power defined per unit surface area. Okay. When you come to energy balance, which is the basic way we do this analysis, we will go per unit surface area, because that is what is relevant for energy balance. Now, this graph just re-establishes that issue. Now, we are going to introduce a concept of black body. When I put a subscript b in this E prime b lambda, I mean I am talking about a black body. Black body is an ideal body defined for convenience, which is a reference body in radiation. Any other surface is always compared to a black body. Okay. So, let me go forward and So, whenever you define any quantity in radiation, we start with directional spectral quantity. Okay. That is the basic starting point. Then we can integrate over angle, we get the hemispherical quantity, average over theta and phi, or you integrate over wavelength, you get hemispherical total. Then you can do at the top the wavelength integration, or at the bottom angular integration, you get the final quantity, which is hemispherical total. This is the quantity of interest to us. This is what will control the energy balance of the earth. But we start from a basic quantity, which is well defined and well understood. From there, through angular integration and wavelength integration, or wavelength and angular, does not matter which way you do it, ultimately you arrive at hemispherical total. So, this is the quantity of interest to us, this is the quantity, basic quantity from which we start. Same thing is true for intensity. We start with directional spectral intensity, and after angular and wavelength integration we come to hemispherical total, or you can do the reverse, wavelength and angular, we still come to this quantity, which is of interest to us in energy balance. Now, I just repeated that, and I want you to remember that in the directional spectral quantity we can define per unit wavelength or per unit frequency. Okay, frequency also is used by many people. So, its frequency, you take the energy at every angle, every frequency, divide by solid angle, divide by surface area for emissive power, and per unit frequency. So, this quantity has different units. It is watt per meter squared per second minus 1 per steradian. Steradian is a unit used for solid angle. Radian is what you learnt in school for angle in 2 dimensions. For angle in 3 dimensions, it is steradian, that is all. And the way we define the directional spectral emissive power in frequency coordinate and directional spectral emissive power in wavelength coordinates, these two are related by this equation. Okay? Because once you multiply here by d lambda, here by d nu, both are watts per meter squared per steradian, and they have to be equal, and the minus sign is coming is because we increase wavelength, frequency has to go down, because nu into lambda is a constant. So, lambda goes up, nu goes down. Okay? Now, what is a black body? Black body is a body defined as an ideal body that absorbs all radiation incident on it at all wavelengths and all angles. Okay? This is special body defined for convenience. It does not exist in the laboratory, but it is a very important reference body. Okay? But remember, any surface that is black in color is not a black body. Black body is one word. Okay? It is a single word, ideal body. So, why is any body which is black in color not a black body? Because when we see a body in the visible with our eyes, we do not know how it looks in the ultraviolet or in the infrared. Until we check that the body absorbs all radiation at all wavelengths from X-rays to microwaves, it is not a black body. Okay? So, very important distinction between a body which looks black in color and a black body. Black body is one word, remember that. Okay? Is defined as an ideal body which absorbs radiation in all wavelengths from X-rays to microwaves. Okay? And such a body does not exist in the laboratory, but it is a convenient reference body. Now, there are all these wavelengths of electromagnetic radiation, even gamma rays, which we will not talk about in this course, X-rays, ultraviolet, visible, which you know all about because our eyes can see the visible light. Then we have infrared, and of course, radiation emitted by earth, thermal radiation, and microwave, which is a wave all of you are familiar with because your mobile works in the microwave domain. Okay? But in this course, the focus is on ultraviolet, visible and infrared primarily, because that is where sun emits radiation and earth emits radiation. Okay? Now, to make sure you really understand the fact that something black in color may not be black in other wavelengths, I have shown a picture of a plastic sheet which is black in color. It is not a black body because the same sheet in the infrared is transparent. Okay? It does not absorb the black light. So, this is not a black body. It is black in color in the visible, but it is not a black body. So, make sure that you understand the distinction between a body which is black in color and a body which is a black body. Okay? You have to look at the given surface at all wavelengths before you declare it a black body. Okay? A black body, in addition to absorbing radiation all wavelengths from X-rays to microwave, it also emits radiation equally in all directions. That is, the directional spectral intensity of a black body is independent angle theta and phi. Okay? That is by definition. Real surfaces do not behave that way, but for this course, for convenience, we will assume real surfaces do not show angular dependence. Okay? That is an approximation that will cause some errors, but in this first course that will not be too large a consequence. But as you go to advanced courses, you have to take into account the fact that real surfaces do have angular dependence of intensity. Okay? So, if you assume that the directional spectral intensity of a black body is independent angle, you can take it out of the integral over angle, and this integration all of you can do. It is very simple, trigonometry. You first integrate over the angle phi, which gives you 2 pi, then integrate over this gives you half, so you get pi. Okay? So, pi is the integral. So, finally, hemispherical spectral emissive power of a black body is pi times the directional spectral intensity, which is a very important equation. We are going to assume this is also true for real surfaces, but this is an approximation. This is always true because black body by definition its intensity is independent angle theta and phi, but a real surface this is an approximation which we will use in this course, but in advanced courses you may see more complicated assumptions. Now we come to a very important law which was developed by Max Planck in 1901, which was a major step in the development of quantum mechanics. All of you have heard about it in your high school, and Planck showed that the hemispherical spectral emissive power of black body is of this form. He derived it based on some assumptions. Okay? And this is a very elegant result he got. His derivation has been questioned, but Einstein, the great scientist, he came up with a better derivation, and that is more easy to understand than the one of Planck's. And but even Einstein's derivation combined quantum mechanics and classical physics. The Indian scientist S. N. Bose, at a very young age, in the mid-20s, he wrote a letter to Einstein showing that he can derive it better using only statistical thermodynamics. Now, I won't derive this in this course because it requires a knowledge of both quantum mechanics and statistical thermodynamics, but those of you who have background, please go look at it, because the derivation that S. N. Bose arrived at is the most elegant one. Okay? So, we will assume that this is always true. Initially, a lot of people had doubts about whether this is true, but today we can look at a black body not in the laboratory, but in the universe. If you go outside at night and look at the radiation coming from the sky, not from the stars, but between stars where the sky is dark, we get what is known as cosmic background radiation. This is radiation emitted by the Big Bang a long time ago, 4.5 billion years ago, and that radiation still can be seen, and that comes from all directions in the sky, equally in all directions almost, and that behaves like exactly like a black body. Okay? And people have measured it both at the ground and more accurately from satellites, and that shows that this formula derived by Planck more than 123 years ago is exactly valid. So, this law is accurate to many decimal places. So, people who had doubts about this law were all had to accept that Planck's equation is valid everywhere in the world and in the universe. Okay? So, you can assume this law is like the laws of physics, perfectly known, there is no approximation. Okay? So, this law was derived in the frequency space, which is convenient, but we also need the same equation in the wavelength coordinate. So, to do that, we use this identity which connects E lambda by d lambda to E nu by d nu, and this I already had mentioned. So, you can take this, you can put it here, and since nu into lambda is equal to c, you can derive d nu by d lambda, assuming c is constant, and you will get this equation. Okay? You can derive this from this, and so this is the form used in many occasions. This form also is used. This convenient for some purpose, this convenient for other purposes. So, we will use this form of the equation of hemispherical spectral black body emissive power in wavelength coordinate. Now, if you plot this function as a function of wavelength at different temperature of the black body, the function is like this at various temperatures. Notice that this function is not symmetric about the maxima. So, there is more radiation to the right of the maxima than to the left. Okay? And so, if we take the equation for E lambda b and differentiate it and set it to 0, you will get the maxima. It occurs at a location where lambda into T is equal to 2898 micron Kelvin. Now, the location of this maxima was discovered by a scientist called Wien, Wien, before Planck derived his formula. Okay? And so, this is called Wien's law, and this is a very important law in black body radiation. And the main thing is that the black body radiation function is such that to the left of the maxima we have 25% of the radiation, To the right you have 45%, 75%, to the left 25, to the right 75. So, it is a long tail, and this is very important. So, when you look at the maxima of a black body radiation, you must remember that most of the radiation is to the right of the maxima, not to the left. Okay. Now, this is again rewritten Wien's displacement law is called. The location of the maxima is 2898 by T in degrees Kelvin, is in micron. So, suppose you look at the temperature near the earth's surface, which is around 299.8, the peak of the black body radiation will be at 10 micron. Okay. On the other hand, if you look at temperature close to that of the sun, which is around 5696 Kelvin, it will be around 0.5 micron. So, sun's radiation maximizes around 0.5 micron, right in the middle of the visible, while the radiation emitted in the temperature relevant to us on the earth is around 10 micron. This is a huge difference, right. So, this plays a very important role in understanding Earth's climate, because the properties of the atmosphere and the surface, properties of ice and snow are very different at 10 micron and 0.5 micron. For example, all of you know that the snow is white in color, okay, because we see it in the visible. But the same snow, if you look through an instrument at 10 micron, the snow will look black, it will not reflect any radiation. So, the property of snow is very different at 10 micron compared to 0.5 micron. You have to account for it properly in your calculations. If you assume that the snow behaves the same way in the visible and in the infrared, you will go completely wrong. Okay. So, do not ever be deceived by what you see in the visible. Unfortunately, we human beings can see only in the visible, okay? But a surface has very different properties in the visible and in the infrared. So, through instruments we know how the reflectivity or absorption of surface depends on wavelength. But we judge a surface by its visible properties, and we saw that a plastic sheet which looks black in color is actually transparent in the infrared. So, this is an important thing to remember, which affects the way we understand Earth's global mean temperature. Okay. Now, we have looked at black body radiation at a given wavelength, but the quantity of interest to us is how much radiation is there in a given range of wavelengths. For example, visible 0.4 to 0.7 micron. For that, we have to take the black body radiation, integrate over the wavelength of interest, and if you want to know what fraction lies in this range, divide by the total integral 0 to infinity. This is called f, fraction of black body radiation which lies in a given wavelength range. Okay. Now, to do the integration is convenient to recognize the fact that if you divide E lambda b by t to the power of 5, this function depends only on lambda t. Okay. Lambda t is here, lambda t is here, rest are all constants. Okay. So, that makes integration easier. So, we define radiation lying between lambda 1 t to lambda 2 t as lambda to lambda t of this function. Okay. Okay, when you do that, let us understand what is the integral when you integrate from 0 to infinity. Okay. You can divide in the frequency coordinate or the wavelength coordinate, they will get the same answer, no difference. Let us look at the integration, and this can be easily done. I have shown the steps. We take out all the quantities which are not functions of wavelength outside the integral. We define a non-dimensional quantity h nu by k t, okay, which is eta. So, we get inside the integral eta cube is eta minus 1. Okay. So, eta is nothing but frequency in a non-dimensional form. So, this integral is very well known. Those of you who have taken a course in complex variables, you know that this is nothing but pi to the 5 by 15. Okay. If you don't know that, you can today go on the computer, integrate this numerically, you get the same answer. Okay. So, the total emissive power of black body integrated over all wavelengths is equal to this quantity. This is a very important equation. In this equation, this quantity which is in the front, which is a universal constant, is called sigma, the Stefan-Boltzmann constant. Okay. So, this was only derived empirically from the laboratory. Today, we can obtain this value just from the value of the Boltzmann constant, the Planck's constant, and the speed of light. All are universal constants. That means the value of sigma, the Stefan-Boltzmann constant, is a universal constant, same all over the universe, not just on Earth. Okay. And this value is 5.67 into 10 to the power minus 8 watts per meter square degree Kelvin to the power of 4. It is a very important quantity. We will keep coming across it in this course. Okay. Now that we have done all this, we would like to know how much radiation lies between different wavelength ranges. Okay. And I will go further and then come back to this equation. So, based on the Wien's displacement law, we can ask at 300 Kelvin how much radiation lies in different wavelength range. So, if you go back to the previous slide, you say that you see that from 0 to 1448 magnitude Kelvin, only 1% of the radiation lies in this range. Okay. So, if you take a T of 300, you will get 148 by 300, which is 4.52 micron. So, at 300 Kelvin, radiation below 4.8 micron is only 1%. Okay. And if you take 23220 divided by 300, you get 77.4 micron, which is the wavelength above which there is only 1%. So, I am trying to find out where 98% of the radiation lies. That is, I want to ignore radiation which is at the lower wavelength range only 1% and above net 10%. And for a black body at 300 K, it is between 4.82 and 77.4. Okay. So, what it tells us that a black body at 300 Kelvin, most of the radiation will lie between 4.82 micron and 77.4 micron. Now, if you take sun temperature around 6000 Kelvin, is a round number, then you can do the same thing. You will see it is between 0.24 micron and 3.87. The key point for this particular example is notice that the radiation emitted by a black body at 6000 Kelvin lies between 0.24 micron and 3.87 micron, while that emitted by a black body at 300 Kelvin is between 4.2 and 77.4. They are almost mutually exclusive. That is, the radiation emitted by a black body at 300 has almost no radiation overlapping with that from the sun, which is assumed to be at 6000. This is a very important conclusion, that the radiation emitted by surfaces on Earth are at a totally different wavelength range than by the sun. So, this concludes this lecture, and we will continue on this topic in the next lecture.